morning, everyone. Hello. Welcome back to yet another class of further math. Whoa. So today we're going to be doing proofs. Specifically, we'll be looking at two kinds of proofs. Proof by contradiction and proof by induction. So what you've done so far in AdMath is you've only seen proof by deduction, whereby you start with a true premise, something that you know is true, and then you work your way to another statement which is also true. Kind of like in trigonometry, where you start on the left hand side, you work your way to the right hand side, and then you go shown, done, right? That's an example of proof by induction. So let me show you another example. Hang on, let me just put that up. Okie dokie. Oh wait, actually, I kind of forgot something. Hang on, give me a second. Wow. So, have you guys tried any of the series questions from last week? Hopefully you find them okay. If there's anything, feel free to ask me. That's what I'm here for. Okay, going back to this. Right. So, suppose I have a triangle, some random triangle that I've drawn like so. Okay, and let's label this A, B, and C. So what is the sum of the internal angles of the triangle? Well, I'm sure you know the answer to that. It's 180, but how do we prove that it is 180? All you got to do is draw a line like so, and as you can see, this angle here has to be A because they are alternate angles. Let me get my pointer out. Make my pointer chunky. There we go. You can see this and this, they're alternate angles, therefore they must be the same. And then you also have this guy here, which is another alternate angle with C, so they must be the same as well. Therefore, A plus B plus C must be 180 degrees. So this is I think you would call this proof by deduction. There are actually 11 kinds of proofs, as far as I know, looking at Wikipedia. A lot of them I'm unfamiliar with. The ones that I am familiar with, that the ones that you should be familiar with if you are doing further math, would be proof by deduction, induction, and contradiction. So we will mostly be using induction and, well, you'll be mostly using three of them. Okay, so another proof by induction, not proof by deduction, sorry, that you can do is this one here. So we're going to start with this statement. The square of an odd number is also an odd number. Okay, so this is our statement. So how do we prove that this is true? Well, an odd number can be written as 2k plus 1. I'm going to call this 2k1 plus 1, where k1 is some integer. Could be a positive or negative integer, it doesn't matter. The symbol here is the set for integers. For real numbers, you use this symbol. For complex numbers, you use this symbol. And there's a bunch of other symbols. But for now, we're interested in this symbol, integer. And then this symbol here means is an element of. Okay, so that's what the actual meaning is, but we can think of this as is. So mathematically, we are supposed to think of this as is an element of, because this is part of set theory, but this is just mathematical jargon. You can think of this as is. So k is an integer. Essentially, that's what this statement means. Okay. Next up, we're gonna make another odd number. So 2k2 plus 1. This is going to be k2 is also another integer. So these two numbers, 2k1 plus 1 and 2k2 plus 1, they are both odd numbers, right? Because if I take any integer multiplied by 2, it's going to give us an even number. And if we add any even number by 1, we're going to get an odd number. So this, by construction, has to be an odd number, these two numbers here. Okay, so if we add two odd numbers, for example, let's say I take this guy and add it with another odd number, what am I going to get? I'm going to get 2k1 plus 2k2 plus 2, which is essentially 2 bracket k1 plus k2 plus 2. And as you can see here, I take 2 times any number, because an integer plus an integer is just some other integer. If I multiply by 2, I get an even number. And if I take any even number and add it with 2, I will get an even number. So the sum of odd numbers must be even. So this is another kind of proof by deduction that you can do, a very simple one. Okay, but this is not really what we are interested in. What we're interested in finding is to show that the statement that when you square an odd number, you also get an odd number. So let's say we take 2k1 plus 1 and I square it. What do I get? I'm going to get 4k1 squared plus 4k1 plus 1. Then we can take out the 2 here, which is going to give us 2k1 squared plus 2k1 plus 1. As you can see, this is actually just some random integer, because I take an integer squared times 2 plus 2 times the integer. I'll just get another number, right? It's just another integer. If I multiply by 2, I'm going to get an even integer. And if I add it by 1, it's going to be an odd number. Therefore, the square of any odd number is also odd. So, proof by deduction. Okay. Now, next up, we're going to look at something called proof by contradiction. Okay, so these two here that we have done so far is called proof by deduction. Now we're going to look at proof by contradiction. So for proof by contradiction, you usually start with a premise. That is false, and then you work your way to a contradiction. So if you get a conclusion that is a contradiction means it doesn't make any sense, or it doesn't make any sense. So if you get a conclusion that is a contradiction, that means your premise must be incorrect. So suppose you say, let's say we look at this triangle again. So suppose, so this is an example here, suppose that A plus B plus C is greater than 180 degrees. Okay. Then the angle, the total angle of a straight line must also be greater than 180 degrees, because this is A plus B plus C, which doesn't make sense. So this is a contradiction. Therefore, A plus B plus C must not be greater than 180 degrees. So that's a very, very basic way of showing that it's not this. But it doesn't necessarily mean that A plus B plus C must be 180 degrees, right? Because there are two possible other outcomes. A plus B plus C could be equals to 180. A plus B plus C could be less than 180. So usually you only employ proof by contradiction for a statement that can be either true or false, so that if you can rule out the one that is, if you can rule out one of them, that means the other one must be true. So let me show you another example. Let me just move that over here. So do you guys remember what a rational number is? What is the definition of a rational number? Have you guys come across this term in math? What is a rational number? No one knows what a rational number is? What? Okay. I'll tell you what a rational number is, I guess. A rational number, one integer divided by another. Yes, that is correct. That's right. So a rational number is a number that can be expressed in P over Q, where P and Q are integers in the lowest form. For example, 10 is a rational number because I can write 10 as 10 over 1. 2.5 is a rational number because I can write this as 5 over 2. 1.33, and then it sort of goes on forever, is also a rational number because I can write it as 4 over 3. Pi is not a rational number because this actually goes on 3.142. I can't remember the rest, but it goes on forever. So you can't write it in a fraction like this in the lowest form. Okay. I think you might have come across certain textbooks where they say pi is approximately 22 over 7. But pi is actually not 22 over 7. It is very close to the number 22 over 7, but pi is in fact slightly less than 22 over 7. So if you're interested, I can show you that in a bit, but for now, let's not get too distracted and we'll come back here. So let me get rid of this. So pi is not a rational number. Now, another I suppose you could say, kind of famous irrational number is square root of 2. So square root of 2 is actually an irrational number, and this was discovered during the ancient Babylonian times. And allegedly, someone was actually murdered because he revealed that root 2 is an irrational number. I think his name was Hippasus or something like that. Because a long time ago, there was a cult. I think it was a cult worshipping, or rather, I suppose you could say they're worshipping numbers in general. The cult centered around Pythagoras, right? The guy who, did the Pythagorean theorem. So they believe that all numbers are rational and all numbers can be expressed in this form. And then someone revealed that root 2 cannot be expressed in this form, and then they were so angry that they basically killed him. So let me show you the proof. See, the one thing nice about mathematical proofs compared to science is that mathematical proofs are eternal. They can withstand the test of time. So this was done, 2,000 something years ago, and it's still something that we are learning today. However, for science, I'm not saying science is not true. Science is more likely to be true than most things, but I'm saying that the scientific method constantly improves on the existing model that we have of the universe, because science exists to explain natural phenomenon, right? So we see something and then we say, oh, okay, we construct a model that is able to explain this natural phenomenon. So a long time ago, when I was your age, when I was learning about the atom, we learned that the atom is like a little ball in the middle with some nucleus, and then we have these electrons that are whizzing around the nucleus, kind of like this. They are sort of moving in an orbit, right? This was the atomic model that I learned back when I was in school. But apparently, this model doesn't really explain a few quirks in nature, so they had to come up with a better model, which is one of the nice things about science, because it's flexible, right? If someone can prove that there's something wrong with the model, then the scientific community as a whole will have to come up with a better model. So we now know that this model is in fact incorrect, and the actual model kind of looks like, there's like a nucleus, and then there's like a fuzzy wave of electrons around it. And this actually comes from quantum physics, which you will learn a little bit, just the surface, if you're doing physics in A2. So that's just how science works, But for math, if you prove something is true, it's going to be irrefutably true for the rest of time. It's just true forever, which is nice. So we're going to show that root 2 is in fact irrational. And how do we do that? Well, we're going to use proof by contradiction. So we're going to start with the premise or the statement that root 2 is irrational, and see if we can arrive at a contradiction, right? So we're going to say root 2 is equals to p over q, because we're assuming that root 2 is rational. So we can write root 2 as p over q, right? So we're going to move, you know what, let me just use a over b instead. I think I like a over b better. That's a over b. So a must be equals to root 2b. If I square both sides, I'm going to get a squared equals to 2b squared. Okay, so what does this statement tell you? It tells you that a squared must be even. Oh, oops, I missed an e here. All right, a squared must be even, because a squared is 2 times of b squared, and b squared is just some random integer. So a squared must be even. So going back to this little thing that we proved earlier, we showed that the square of an odd number is also an odd number, right? So the square of an even number must be an even number. And you can actually prove this very quickly. Let's say you have 2k, this is some even number, and I square it, I will get 4k squared, which is actually 2 times 2k squared. So the square of an even number must also be even. Okay, which means if a squared is an even number, a must be even. Cool. So if a is even, that means it is divisible by 2, then b must be odd. So b must be odd. So why does b have to be odd? Because p over q, or this expression here, this fraction here, must be in the lowest form. So we can't leave it as, you know, something like 2 over 4. This is not considered the lowest form. The lowest form means you have to simplify it, so you get something like 1 over 2. Or maybe something like, 2 over 5. So you can see that any fraction that is in the lowest form, it usually comes in either even and then odd, or odd and then even. It never comes in even, because if it's even, that means both of them must be divisible by 2. So you would always simplify to odd even, or even odd. Okay, so since we know that a must be even, because a squared is even, therefore b must be odd. All right, cool. Now, the next thing we're going to do is you can see that because a is even, which means a squared must be a multiple of 4. Right? So think about this. If a is even, that means it is a multiple of 2. So if you're squaring it, then it has to be a multiple of 4, at least. Like for example, I take, I take 4. If I square it, I get 16. 16 is a multiple of 4. If I take the smallest even number I can think of, I get 2 squared, I get 4, which is also a multiple of 4. If I take 8 squared, I get 64, which is also a multiple of 4. So if I take any even number and I square it, I will always get a multiple of 4. So a squared must be a multiple of 4. So what does this tell you? Okay, if a squared is a multiple of 4, then we can actually write this as 4k equals to 2b squared, where k is some integer, right? And if I divide everything by 2, I'm going to get 2k equals to b squared. Oh, so what does that mean? That means b squared must be even, because b squared is 2 times some integer. So b must be even. B squared must be even, sorry. So if b squared is even, then b must also be even. So do you see the problem here? Do you see what's going on? So we now have two statements that contradict each other. We have a statement that says b must be odd, and we have a statement that says b must be even. And we know that a number cannot be both odd and even at the same time. Therefore, something must be wrong. And what is the thing that is wrong? The assumption that we made at the start. So we made the assumption that root 2 is rational. But because there is a contradiction that arises from this statement, that means the statement must be wrong. So if root 2 is not rational, that means it has to be irrational. Okay, so therefore, root 2 is irrational. Whoa! Proof by contradiction. So we prove something is the way it is by arriving at a contradiction. Where does k come from? K is just any integer. So because we know that a squared must be a multiple of 4, so I've just written this as 4 times some integer. So k can be 1, 2, 3, 4, 11, any integer you want, but it has to be 4k because it is a multiple of 4. So, yep, there we go. Okay, so let me show you another really cool proof by contradiction. So this one is actually done by Euclid. In, I think it was like 300 BC. So he proved that there are infinitely many prime numbers. So this proof is actually 2,300 years old. Whoa. Okay, so let me just move this down here. So we're going to try to prove that there are infinitely many prime numbers. So the statement that we are trying to prove is that there are infinitely many prime numbers. No worries, no worries. So this is a bit of a weird statement to prove because it's like trying to prove there are infinitely many even numbers, right? How can you show that there are infinitely many even numbers? So maybe we'll start with that first, actually. You know what? Let's start with something a bit easier. Let's say we start with the statement where we are trying to prove we have infinitely many even numbers. So let's say the statement is there are infinitely many even numbers. Okay. So the way you go about proving this is by using proof by contradiction. So we're going to start with a premise, which may or may not be true. If it's not true, we will arrive at a contradiction. So we're going to start with a premise and say that there are finitely many even numbers. Okay, and then the full list of even numbers is we're going to say 2k1, 2k2, and eventually it goes all the way to 2kn. So this is the full list of even numbers, where 2kn is the largest even number. I mean, obviously we know intuitively that this has to be false, but how do we prove that it's false? Well, all you gotta do is you say 2kn plus 2 is actually 2 bracket kn plus 1. So this is actually an even number. This is an even number. And then you can see that 2kn plus 1 must be greater than 2kn, which is a contradiction, because this directly contradicts what you've just said here. You're saying that 2kn is the largest even number, because this is a full list of even numbers, and we're taking the last one here to be the biggest one. But this contradicts that statement. Therefore, this premise must be false. Therefore, this statement must be true. There are infinitely many even numbers. So this is a very basic kind of proof. Okay, so now we're going to use the same method, and we're going to try to prove that there are infinitely many prime numbers. So what is a prime number? Can anyone tell me what a prime number is? I suspect you might have learn of prime numbers, maybe in year 9. What is a prime number? Can be divided by itself and 1 only. Yes, that is correct. A prime number can only be divided by itself or by 1. Can't be divided by anything else. For example, numbers like 3, 5, 7, 11, 13, and so on, right? So do we have an infinitely many prime numbers or just finitely many? Well, let's try to prove this. We're going to start with a premise, and we're going to say that there are finitely many prime numbers. Okay, and then we're going to say that the full list of prime numbers is P1, P2, P3, and it goes on all the way to some prime number pk. So pk is, by definition, the largest prime number. Yeah, this is the largest prime number. Okay, so that's the full list of prime numbers because we're assuming there's a finite number of prime numbers. So what we can do now is we're going to construct a new number. We're going to call this number q. So q is a number such that we multiply all the prime numbers together, and then we add 1. Okay, so that's how we construct this new number here. So this new number q is actually not divisible by any of these prime numbers. Okay, let me just show you what I mean. For example, let's say we have 2 times 3, right? 2 and 3 are prime numbers. We're going to get 6. So any number, any integer that is not a prime number is made up of prime numbers. Yeah, because you can see 6 is not a prime number. It's made up of 2 prime numbers, 2 and 3. Let's say we pick another non-prime number. Let's say 15. 15 is 3 times 5. Let's say 24. 24 is 2 times 2 times 6. And 6 is actually 3 times 2. So we actually get 2 cubed times 3. So any integer that you choose that is not a prime number is made up of prime factors. This is called the prime factorization theorem. You can break down any number into prime numbers. So you can think of prime numbers as the building blocks of numbers, kind of like DNA being the building block of life. So unless it is a prime number, so a prime number can only be divided by itself or 1. Okay, so the prime factorization theorem doesn't apply to prime numbers. Now, if you take any 2 prime numbers or any bunch of prime numbers, let's say 2 times 3 times 5, and then you add 1 to it, what are you going to get? Let's see, 6, 30, we get 31. So we might get a prime number, right? Because this, you can see that 31 is not divisible by 2 or 3 or 5. Therefore, it has to be some prime number. And the way you think about this is, imagine I have a segment. So this segment represents a number. So let's say the number is 30, okay? And then let's say the number is 4. Let's say the number is 4. So we have 1, 2, 3, 4. So the number 4 is divisible by 2 because I can split it into 2 equal parts like that. Okay. it is also divisible by 1 because I can split it into 4 equal sections. I can do this with any kind of number. So let's say I use something bigger. Let's say I use 10, or let's say I use 10. Okay, I can. So 10 is divisible by 1 because I can split it into 10 equal sections. 10 is also divisible by 2 because I can split it into 5 equal sections. 10 is not divisible by 3 because I can't split it into equal sections. I can go something like 3 here, and then 6 here, and then 9 here, but then from here to here is a 1. So this section is not the same length as these are the sections, therefore it is not divisible by 3. So whenever you want to divide something, you must be able to split it into equal sections. So let's say I have 10, okay? And we know 10 is divisible by 5. So if we add a 5, we get 15. 15 is also divisible by 5 because we've added a 5. So we've added an equal section of 5, right? If we add another 5 to this, we get 20, which is also divisible by 5. So as long as we're adding 5s, whatever number that we construct is going to be divisible by 5. However, if we add a 1, then it's not divisible by 5 anymore because that 1 is not going to be able to fit the 5, if you see what I'm trying to get here. So that's the trick, right? See, if you're adding a 1 to the end, that means whatever number that you get will not be able to fit any of these prime numbers because 1 is smaller than the smallest prime number, 2. So you're not going to be divisible by 2 or 3 or 5 or any of these subsequent prime numbers that you've put in because you're only adding by 1. If you add by 2, then it's going to be divisible by 2 because you now have 2 sections of 2 in there. Okay, and you're taking 2 multiplying by a bunch of numbers, which is going to give you an even number, and you add it by 2, which is going to give you another even number. So in the end, this guy is going to be divisible by 2. I can mention the same thing if I add it by 3. If I add it by 3, then I have 3 times some multiple of 3, and then it's going to be divisible by 3. But if I add it by 1, then none of these things are going to be divisible by this number here. Okay, so we can get a prime number, but let's say we go 2 times. Hang on, where's my number? 2 times 3 times 5 times 7 times 11, and then I add it with 1. Well, what am I going to get? 2 times 3 times 5 times 7 times 11. Let's say we times it one more time. Let's go times 13 plus 1. We are going to end up with 30031. So 30031 is actually 59 times 509. So you can see here in the first case, we end up with a prime number. But in the second case, we actually end up with a non-prime number. And you can see the prime number that we get, 59. Right, so 59 is not divisible by 3. 59 is actually a prime number. So you can see that we end up with a new prime number that is not in the list that we have used to construct this number. Okay, so having made that observation, what can you tell about this Q here? So Q, this number here, must be either a prime number or a non-prime number. So there are 2 possible outcomes, either a prime or a non-prime. So if this thing is a prime number, that means our premise must be false. There are finitely many prime numbers, and this is the largest prime number. So if we multiply all these together and add 1, obviously Q must be bigger than the largest prime number, which would invalidate our premise. So what if Q is a non-prime number? If Q is a non-prime number, we would actually get a number that is made up of some prime factor, and one of the prime factors has to be a prime number. Well, I mean the prime factors have to be prime numbers, right? Because any non-prime number is made up of prime numbers. So if this is a non-prime number, then it has to be made of prime numbers. And one of the prime numbers would be not in the list that's given, as you can see over here. Therefore, this prime factor must be larger than the largest prime number, or it's not in the list that it's given. So this is not a complete list, which means there are more of prime numbers than what we have postulated over here. So in either of these cases, this premise must be false, which means there is a contradiction, so this statement is actually true. There are infinitely many prime numbers. So that's how you prove you have infinitely many prime numbers. And there you go, a 2,300-year-old proof by Euclid in 300 BC that is true to this day and will be true for the rest of time. Okay, so yeah. Okay, what shall we do next? Let me think. Wow. Yeah. Yeah, it's really quite a beautiful proof, isn't it? See, math is all about recognizing patterns and logical deduction. It's a very pure form of, I'm just sort of digressing here. Okay, let's move on to the next one. So the next one we're gonna do proof by induction. Is there anything else I can show you guys? Let me think. Okay. Here's something interesting. So this is probably something that you might have thought about. Is it true that everything in maths can be proven? Can you come up with a proof for everything in math? Right? And surprisingly, the answer is no. There are certain statements in math that cannot be proven. An example is an axiom. So an axiom is a statement in our framework of math that we assume to be true. For example, if we take any number and we add 0, we will get the same number. Okay, this is just by the definition of 0. So this is just a statement that we assume to be true without having to prove it. And if you take a number and you add it with another number, you get 2 times a number. That is also like an axiom, I suppose, because you don't have to prove that it's true. We know it's true, right? So math is actually made up of a bunch of axioms. You can think of them as like the building blocks of math. And then everything else comes from these little axioms or the combination of these axioms. And but there are certain things in math which may not look like an axiom, but is actually something that we have to assume is true. How should I explain this? So there are certain statements in math that cannot be proven. So this is actually done by someone called Gordell, and this theory is actually called Gordell's incompleteness theorem. So he managed to prove that not all statements in math can be proven, which is quite a mind-boggling proof because he's using the framework of math itself to prove something within the framework of math itself, which is kind of like a weird inception kind of thing, but it actually works, and it's quite an ingenious proof. But I need to refresh my memory because I haven't done this in a while, so maybe I'll show this to you next class. But it's very, very clever. But anyway, let's continue with proof by induction, which is the main content for what we're going to do today. Proof by induction. So proof by induction comes in a couple of steps. So the first step you want to do is you want to prove the base case. Prove the base case. I'll explain what these mean in a bit. And then after that, you want to do the inductive step. And then you write your conclusion. And you usually only use proof by induction for statements that are true for integers. Well, I shouldn't say integers, for natural numbers. So n here is a natural number. What is a natural number? A natural number is a positive integer. So things that we can count naturally with our fingers. Right, 1, 2, 3, 4, 5, 59. As long as it's a positive integer, it's what we define as a natural number. So natural numbers do not include 0. Okay. So let's start with, okay, you know what? I'm going to use some examples from the textbook. Some good examples here. Let's go with that. Oh, okay, we can actually just use this. Actually, you know what? Let's use S2. No, let's do S1. Okay, so proof by induction that the sum of r equals 1 to n is equals to n over 2 n plus 1. So we've done this in one of the earlier chapters. If you recall, if you sum up positive integers, you will get this formula right here. So we're going to try to prove this by induction. So the way you do this is by starting with the base case. So firstly, the base case. So base case we usually write as h0, comma. Base case means we say if n is equals to 1, is the statement true? Okay, so we go the sum from r equals to 1 to 1, r, that's going to be 1. Right, because we are summing up we're summing up this r here once. So we're just getting 1. Okay, so left hand side is going to give us this. What about the right hand side? Well, we're going to get 1 over 2 and then 1 plus 1. So we're going to get 1. So therefore, yes, base case is valid or true. Okay, so we've proven that when n equals 1, the statement is true. So the next thing we're going to do is hk. So if n is equals to some unknown k, we get r equals 1 to k, r equals to k over 2, k plus 1. right? So we're just making another statement here. We're just saying that if we replace n with k, we just get this guy. So next thing we're going to do is hk plus 1. So if n is equals to k plus 1, we expect to get k plus 1 over 2 and then k plus 2, right? So this is what we expect to get. But do we actually get this? So we can't just replace the n with k plus 1 and then get this, and then we say, oh, yes, we get it. Yes, we are done. No, we can't do it like that. So the way proof by induction works is you have to start from this guy here. Okay, let me just show you how to do this. I think once I write it out, then it will make a bit more sense. So this is what we are trying to get in the end. Okay. Then we get r equals 1, k plus 1. R is actually this guy plus this guy. Okay, so we need to show that we can get this guy from this guy if we replace n with k plus 1. But you can't immediately jump from here to here. This is the goal that we are trying to get to. So that's going to give me k over 2, k plus 1. So this guy here is actually from this guy. Okay, so this one we assume to be true. So the next one, we're going to get k plus 1 over 2. Wait, hang on. Oh, we just get k plus 1. There we go. Okay, because we're just summing up from k plus 1 to k plus 1. So we just get k plus 1 and we stop. Okay, so now we're gonna try to simplify this and see what we get. We get k squared over 2 plus k over 2 plus k plus 1. Which means we get k squared over 2 plus 3k over 2 plus 1. We can factorize a half out, so we get k squared plus 3k plus 2. And then we factorize this even further, we get kk and then 1, 2 plus plus. And as you can see, we get what we want. There. So the point of us doing part 2 here, so let me just go through part 2 again. So for part 2, we start by saying that if we replace n with k, we get this. And we're going to assume that this is in fact true. So we know two things is true so far. Two things are true. We know that this guy would give us this, and we know that when n equals to 1, we get this guy. So the next thing we need to show is that this guy actually gives us this. Okay, so we're going to start with this, and we know that this is actually this. And we know this is this because this is true, and this simply gives us this. So if we simplify, we get this. Therefore, we know that this must be equals to this. Okay? So the point of us doing this is to show that, so the whole thing here tells us that if hk is true, then hk plus 1 is also true. And then this one tells us that h0 is true. So now we actually have everything we need to prove this thing is true. And how do we do that? Well, since h0 is true and hk, this one is also true. So since we know these two statements are true, this guy here is actually this statement. I've just sort of compressed it a little bit. So since we know this is true and this is true, therefore h1 is also true. So when n is replaced with 2, then it's also true, because we know that if hk is true, hk plus 1 is true. So it's like a domino effect. Right? So because h0, we know h0 must be true, and this relation is true, therefore h1 is true. And then we can say the same thing. Since h1 is true and hk to hk plus 1 is true, therefore h2 is true. So you see where it's going? It's gonna keep going on and on forever. So if h2 is true, then h3 must be true, because this is true. If h3 is true, then h4 must be true, and therefore h5 must be true, and h6 must be true, and so on. And it goes on all the way to all the positive integers. So therefore, for all n that's a positive integer or a natural number, for all n that's a natural number, for all n that's a natural number, the sum must be true. There. So that's how you prove that this statement is true for any positive integer by doing this domino effect. Okay, so you just have to do two things. The first thing is you prove that the base case is true. The second thing is you prove that this relation hk to hk plus 1 is true. And then you combine these two statements together, and then you get a domino effect. And then you can prove that for all positive integers, this has to be true. There we go. Is that okay? Do you guys get it? Let's do another example. Hopefully. All right. Let me do more examples, and then okay, maybe I'll do a very simple example just to show you. Maybe this might help. Actually, let me see. Maybe I should have started with this. Let's start with a super easy example. All right, let's say we go with let's say we're trying to prove this statement. 2k plus 1 is an odd number. Okay, and then k is natural number. Oh, you know what? Let's say 2k plus 3 is an odd number. There. So let's try to prove that 2k plus 3 is always an odd number. Okay, so we're going to start by doing the base case. So if k is equals to 1, then 2 times 1 plus 3 is going to give me 5. So yes, the base case is true. All right, what about the inductive step? So if k is equals to, let's say, n, or let's say L, whatever. You can use any unknown you want, doesn't matter. If K is L, then we get 2L plus 3. And we're going to assume this is an odd number. Okay? So we're going to assume that this statement is true. 2L plus 3 is an odd number. So now if we have HK plus 1, so the next thing we have to do is we have to link HK to HK plus 1. Okay, so if we have, if K is equals to L plus 1, okay, L plus 1, then we're going to get 2L plus 1 plus 3. All right, which is going to give us 2L plus 2 plus 3, which is 2L plus 3 plus 2. And as you can see here, we have an odd number because we are assuming that 2L plus 3 is an odd number. So we're going to put that in here, right? Because we know this is assumed to be true. So you put that in here, and then we add 2. So whenever you take an odd number and you add it with 2, you will still get another odd number. So this is going to be another odd number. Therefore, if HK is true, then HK plus 1 must also be true. Okay, so now that we have done these two statements here, we know that the base case is true, and we know that the relation is true. Now we can set the domino effect in action. So if H0 is true, and then H1 has to be true as well because of this relation here, right? Because of this relation. So we know H1 has to be true. And if H1 is true, then H2 has to be true as well because, again, of this relation. If H2 is true, then H3 is true. And then this goes on forever. So it's going to cover all positive integers. And that's how you show that. Therefore, the final conclusion that we get is for all k such that k is a natural number, 2k plus 3 is an odd number. And that's how you prove that. So this is a simpler example. Hopefully this helps you see what we're trying to do here. You need to prove one thing is true, and you need to prove the relationship is true, and then you put them together, and then you sort of chain, and you get this domino effect. Okay? All right. Let's continue to another example. Let's see. Let's do this one. Okay, so this one is not very obvious, but I think it's a good example that we can try. So I'm going to try to sum up 1 to n r squared minus 1 equals to n squared minus 1 times n over 3, where n is greater than or equals to 1. Okay, so we want to prove this statement. Prove by induction the following statement. So is this going to be true for all positive integers of n? So usually the hint for using proof by induction is when n is some positive integer. Okay, so let's start by doing the base case. So for the base case, let's see, what do we have? For the base case, we have from 1 to 1, okay, when n is equals to 1. Base case doesn't necessarily mean we have to start with 1. If n here is greater than or equals to 2, then we start with 2. Base case basically means the smallest or the lowest limit. So you choose the smallest number that you can. It kind of depends on the question, yeah? So you have to look at the question and see what the lowest number is. So this guy is going to be r squared minus 1. So from the left-hand side, what do we get? This is the left-hand side, by the way. We're going to get 1 squared minus 1, which is 0. Okay, so from the right-hand side, do we get 0 as well? Okay, let's see. So we get 1 squared minus 1 times 1 over 3. We still get 0. So since the left-hand side is equals to the right-hand side, therefore the base case is true. Okay, cool. We're done with the first part. Now for the second part, we're gonna do HK. So assume that when n is equals to k, r equals 1 to k, r squared minus 1 is equals to k squared minus 1 times k over 3 is true. Okay, so we're going to make the assumption that this guy is true. Now I'm going to try to link that with hk plus 1. So what we are trying to get here, or our goal, is we are trying to show that this guy with the k plus 1 here is in fact going to give us k plus 1 squared minus 1 k plus 1 over 3. Okay, so this is what we are trying to get to. Okay, let's see if we can actually get that. So we have r equals 1k, r squared minus 1, sorry, k plus 1. So this is actually this guy plus k plus 1 squared minus 1. Okay, I've just taken out the k plus 1 and I've just put it over here. And we know this guy is in fact going to be k squared minus 1, k over 3, because we assume that this is true. This relation is true. Okay, so expanding this guy, we get k cubed minus k over 3 plus k squared plus 2k plus 1 minus 1 disappears. Put a 3 in here, so you get 3 here. This is a 6 now. Combining these guys together, we get k cubed plus 3k squared minus k plus 6k is plus 5k over 3. All right. And then, what can we do here? Let's see if we try to expand this, what do we get? We get k squared plus 2k plus 1 minus 1. So we get k squared plus 2k times k plus 1 over 3. Right? So let's try to simplify that by taking out a k. We get k squared plus 3k plus 5 over 3. And you can see here we end up with a little quadratic. So this quadratic is going to give me Oh wait, did I mess up something? Minus k plus 6k. K squared plus 2k plus 1 minus 1. K cubed plus k squared plus 2k squared, so I should get 3k squared. And then, then I should get 2k. But here I got 5k though. That is kind of weird. Nani? Unless I mess up somewhere. K cubed minus k. This one is k squared plus 2k minus 1 plus 1, so cancels. So k squared plus 2k. K squared. So 3k squared. 2k gives me 6k. K cubed plus 3k squared plus 5k. Did I write the wrong question or something? Hang on, let me just check. R squared minus, oh, oops, it's r squared minus r, not r squared minus 1. Oh my god. Okay. So there was a problem with the question. Oopsie. Excuse me. Okay, so this is actually k squared minus k. So this would be r squared minus r, so that would be, yep. It would still be 0, it would still be 0, yep. So base case is still correct. This guy here is going to give me k plus 1 squared minus k plus 1 bracket and then k plus 1 over 3. So that's what we are trying to get. Okay. And then I'm going to do hk plus 1 here. So r equals 1 to k plus 1. This guy is r squared minus r is actually 1 to k plus k plus 1 squared minus k plus 1. Put a little square bracket over there. And we know this guy is in fact k squared minus k times k over 3. And then here we can factorize a k plus 1 out. So we get k plus 1 squared minus 1. Okay. Can put a 3 over here, so put a 3 over there. You can factorize the k out here as well. So we're going to get k squared and then k minus 1. Do we even bother doing that at this point? We need to get a k plus 1 out. So let's see. Oh wait, no. Why did I change this? This should still be a 1. Okay. So this should still be a 1. Hang on, I kind of messed up a bit. I done messed up. There we go. Checking. This should be a 1, this should be a 1, that should be a 1. Okay, all good. Which means this one would be plus k plus 1 squared minus a 1. and then k plus 1 over a tree. Wait, no, what am I doing? What am I doing? What am I doing? They should actually be k plus 1 squared minus k plus 1. Okay. This part is correct. All right. Sorry about the confusion there. Then this guy is actually k plus 1 squared minus 1. The whole thing is bracketed. K plus 1 divided by 3. And then we're going to factorize k plus 1 out here, which is going to give us k plus 1 minus 1. Cool. And then we're going to put a 3 here and a 3 there. All right. Alrighty. So now we're going to simplify this a little. K plus 1 here. The whole thing is divided by 3 plus 3k plus 1 times k. Now we're going to factorize k plus 1 out again. That's going to give me k plus 1 squared minus 1 plus a 3k. Over 3. That's odd. It doesn't quite give us what we want. So we got this part here, we got this part here, but we have an additional 3k. That is strange. Hang on, let me check again. This gives us this guy here. Let me triple check the question. R squared minus r, n, and then n squared minus 1, yep, over 3. Okay, question is correct. So, let's see if I wrote this correctly. When n is k, this should be this guy here, but I replace it with k. Yes. When it's k plus 1, should be the same thing, but I replace k with k plus 1. Yes. And then this guy is actually this guy here. Plus, and then replace this with k plus 1 minus k plus 1, okay. And then this guy is actually this guy. Oh, this guy is this guy. Oops. All right, let's see where I messed up. This guy is wrong. This guy should be k squared minus 1 times k over 3. There we go. So now, let's see. We have k squared minus 1 times k plus 3k times k plus 1 over 3. All right, finally. So we can take out the k here. So we have k squared minus 1 plus 3k plus 3 over 3. So we get k and then k squared plus 3k plus 2. Okay. So is this what we expect to get? This is k here, k there, 1, 2, plus, plus over 3. So is this the same as this? Well, let's try to expand this a bit. We get k squared plus k squared plus k, 2k, and then 1 cancels. Factorize out of k, we get k plus 2, k plus 1 over 3. Yes! So you can see that this guy here is in fact this guy. So we've actually managed to show that this gives us this. We've showed that this gives us our goal. Okay, so therefore, hk would give us hk plus 1. So if hk is true, then hk plus 1 must also be true. So now that we have done these two things, this guy here and this guy here, we can combine them together and show that, therefore, for all values of n, that's a natural number, this summation must be equals to n squared minus 1 times n over 3. And that's how you prove the statement by induction. Yep, so there you go. So you can actually do this for anything that involves positive integers. And if you remember the binomial theorem, the power for the binomial theorem, let's say a plus b and then power of n, this n here must always be a positive integer, right? You did this in AddMath. So you can actually prove the binomial theorem using induction. But I shall save that for another class. You can attempt that on your own if you want, but I'll show that to you next class. But yeah, I think we shall stop here for now. And I think I've given you some exercises that you can try as well. I think it's somewhere right here, over there. There. So here are some exercises that you can try. Should have this. I've uploaded this on Google Classroom as well. So you can try some of these questions. So this one, you can skip this for now. I'll show you how to do this next week, which would be our last class for the bridging program. Hopefully we can finish off the rest of this and then you can start doing some of the past years and get a feel for that. But for now, you can try 1, 2, 3, 4. 4 might be a bit tricky, so I'll show you how to do 4 next class as well. 5 is also a bit tricky, so just try 1, 2, and 3. And if you're feeling adventurous, you can try to prove the binomial theorem with induction. Yep. So we are gonna stop here for today. Hope you found that instructive and interesting. Yeah, this is one of my favorite chapters in further math. I actually have a lot of favorite chapters in further math, but this is definitely top of the list. Okay, so we shall stop here for today. And I will see you guys next week for our last class. And then, yeah, who knows what will happen after that? All right, bye guys.